So the uncertainty principle tells us that energy and position are complementary for an electron. So we know that kinetic energy is equal to 1/2 mv squared. Well, m is the mass and v is the velocity. So the best we can do is to describe the electron's position in terms of basically a distribution map, a probability distribution map. And we call those orbitals. It's a region in space where the electron is likely to be found. And many of the properties of the atoms are related to the energies that its electrons have. So this is the guy who, was talking about the cat. This is the Schrodinger equation, which doesn't look like much like that. These are wave functions. Can't remember the name of that. Anybody know the name of that Greek letter? No? Yeah, I can't remember either. I need to put it in there to remind myself. Anyway, Schrodinger's equation allows us to calculate the probability of finding an electron that has a specific amount of energy at a particular location in the atom. Now, the energy is related to the velocity, right? So we can't know the velocity and the position at the same time. But this allows us to calculate the probability of an electron with this energy being in this place. So the solutions to this equation are wave functions, and these describe the wave-like nature of the electron. So if we take one of those wave functions and square it and plot that out, that gives us the shape of the orbital. We know that the size, the shape, the orientation and space of an orbital are all determined by integer terms in the wave function. There's 3 of them. These were added into the equation to quantize the energy of the electron. Because we know from experiment, from those line spectra, that the energy of electrons is quantized, right? Just like money, 5 cents, 10 cents, 25 cents, 17-cent coin, right? So we put these integers in here so that we only come up with energies that match what we know. So those integers are called quantum numbers. The principal quantum number is given the symbol n. The angular momentum quantum number has the symbol L. The magnetic quantum number has the symbol m sub L. Then there's a 4th one that's not actually an integer, and it's called the spin quantum number. That's m sub s. And we'll be talking about all of those. So let's start with the first one, the principal quantum number. So this is a whole number, an integer, that describes the overall size and the energy of an orbital. And this corresponds to Bohr's energy level. So we can make this work with Bohr's model of the hydrogen atom. So this n equals 1 would be like the n equals 1 orbital. Orbit. Orbit and orbital are different. Orbit is like the planets orbiting the sun. Orbital is this different weird thing. But this would correspond to those different energy levels. So n can be any integer greater than or equal to 1. So n could be 1, 2, 3, 4, those sorts of numbers. The larger that n is, the higher the energy of the electron, and the larger the orbital size. So let's maybe jump back here to the Bohr model real quick. Oh, we've done a lot. There we go. So this is n equals 1, 2, 3, 4, and 5. So an electron with the principal quantum number 5 is going to be in a larger space, and it's going to have more energy. And an electron with a smaller n is going to be in a smaller space and have smaller energy. And so here we were imagining these jumping from one orbit to another orbit, and we could measure the difference in energy based on the wavelength of light that was given off. Unfortunately, it's not quite so neat and tidy as that. So we can describe the energy of an electron in a hydrogen atom using this equation. The energy of, with principal quantum number n, is equal to negative 2.18 times 10 to the minus 18th joules times 1 over n squared. So the energy here is negative because the electron's energy is lowered by its interaction with the nucleus. So the closer the electron gets to the nucleus, the lower its energy is. It's a negative number. Okay? So if n is bigger, then we're dividing here by a bigger number, and the energy is higher, less negative, closer to being positive. So it's kind of like, being underwater. Well, can't make water be red. That's not right. So if this is, sea level, then we can think about, being below sea level. Well, this is, maybe negative 30 meters and negative 20 meters and negative 10 meters. And so an energy of negative 30, a depth of negative 30 is lower, right, than a depth of negative 10. Negative 30 is a smaller number than negative 10, right? Even though 30 is bigger than 10. These are negatives, and so that's just going down under. Not confusing at all. So these are the principal energy levels in hydrogen. When the principal quantum number is equal to 1, the electron has this energy. When it's 2, it has this energy, 3, and 4. And so we see that as we're going up, this is negative 18, and these are negative 19, these numbers are getting larger, they're getting closer to 0. Okay? So this is higher in energy than this one down here. Because a lot of the things about energy we can think of as, balls rolling down hills. It's kind of brown. So if we had a ball and, it fell into the ocean, it's going to roll down. It's going to get lower and lower and lower. That is lower potential energy. Because the potential energy is raising it up higher and higher. Okay, that's the principal quantum number. The second one, L, gives us the shape of the orbital. And so here, L is limited to values from 0 up to whatever n is minus 1. So L is numbers, but we often use letters instead. Of course. Yeah, that makes total sense. There's a lot of history mixed in here. So if L is equal to 0, we call that an s orbital. If L is equal to 1, we get a p orbital, L equals 2, d orbital, L equals 3, f orbital. So you may have heard of these before. 1s2, 2s2, 2p3, or something like that, an electron configuration. Those are those same s's and p's and d's and f's. Okay. And these came about because this was the first letter of a word that described the type of line that was observed. This was principal, and this one was diffuse. And I always forget what S is. but that's why it's not like A, B, C, D. But after this, if you were to go on from F, you would just continue in the alphabet. Okay. So what values of L are possible if n equals 3? So L can be 0 up to n minus 1. So if n is 3, n minus 1 would be 2. And that says that L can be an integer anywhere from 0 up to 2. So it could be this one, right? 0, 1, and 2. Those are possible values. You don't have to like this stuff. The magnetic quantum number gives us the orientation. Is this one straight up and down? Is it sideways? That sort of orientation. How they're aligned with each other. So the values for these, it can be anywhere from negative L up to positive L, including 0. And so this is going to give us the number of orbitals of that shape. So when L equals 2, remember we've got, let's see here, S, P, D, and F correspond to 0, 1, 2, and 3 for the values of L. So if L equals 2, that means we have a D, or D orbitals, right? And then the possible values for M sub L range from minus L, negative 2, all the way up to positive 2, positive L. So negative 1, negative 2, negative 1, 0, plus 1, plus 2. So there's 5 possibilities for that orientation. Each of those corresponds to an orbital. So for D, there's 5 orbitals possible. What about P? For the P, L is equal to 1. And so an M sub L can equal negative 1, 0, or plus 1, which gives us 3 orbitals. And if you've learned any of this before, this is maybe starting to at least sound familiar. For L is equal to 0, M sub L can be negative 0 to positive 0, which is just 0. And so there's only 1 orbital here. And this one's 5, and if you do this one, it's 7. So what values of M sub L are possible for L equals 2? Well, this is dumb because they just did this one on the previous slide. So if L equals 2, M sub L can be negative L to positive L. L is 2, so M sub L can be negative 2, negative 1, 0, plus 1, plus 2. And I'll tell you, I don't like these as exam questions. We need to talk about this. We need to, I've heard about these things. But I've never encountered a situation where I needed to know all the possible values of M sub L. The last one is the spin quantum number. And this talks about the spin of an electron. All electrons have the same amount of spin, and it can be positive or negative. So it's not really like a spinning top, but I give you permission to think of it as a spinning top. Any of you ever play with Beyblades? My kids were super into Beyblades. We've got some in. Well, some Beyblades spin clockwise, and some spin counterclockwise. So that would be like plus 1/2 and minus 1/2 spin for the electrons. Okay. So this describes the orientation of the spin, and we talk about plus 1/2 being spin up and minus 1/2 being spin down. And that's often because we represent these with arrows, and so that would be arrow up and this would be arrow down. So m sub s is always just negative 1/2 or positive 1/2. So if we combine the first three quantum numbers, that's going to describe one orbital. So if we look at orbitals that have the same value of n, like, they are in level n equals 2, those are said to be in the same principal energy level. Orbitals that have the same level values of n and l are said to be in the same sublevel. So again, this is where, kind of imagining the Bohr model. I don't know why we only draw half of it. Obviously, it continues around in a circle. So you can think of these as being the levels that the electrons can be at. So it could be in level 1, level 2, level 3, level 4. Within level 2, there are sublevels, right? There's 0 and 1. So there's 2 sublevels. In n equals 3, there's 3 sublevels. And in n equals 4, there are 4 sublevels. This analogy just came to my head. I'm not sure if it's good or not. So if you think about these as grades in school, right? Grade 1, grade 2, grade 3, grade 4. Well, in grade 3, there's 3 different reading groups. They used to do this, now they do it some other way. It used to be the high-level reading group or the regular group or the low-level reading group, and everybody knew it no matter what you called those levels, right? But there were sub-levels. You were all in whatever grade I said. Did I say second or third? Third, okay. You're all in 3rd grade, right? But you're maybe not at the same level in reading, okay? So those are the sub-levels. So for n equals 1, we have one possible sublevel, that's L equals 1. And within that level, m sub L, the possible values tell us how many orbitals there are. There can only be 1 here. In n equals 2, principal level 2, there are 2 sublevels. The first one, L equals 0, only has 1 orbital. The second one, L equals 1, has 3 orbitals. So they have different numbers for m sub L. Third level, 3 different sublevels. The first one has 1 orbital, then 3 orbitals, then 5 orbitals. This 1, 3, 5 thing did not come about like by chance or something. It has to do with the quantum numbers. So, the number of orbitals within a sublevel equals 2L plus 1. I don't think that's really worth talking about. I think this is good to know. The number of sublevels is equal to the level number. So level 3, 3 sublevels. Level 2, 2 sublevels. List the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? Well, when they're talking about 5D, 5 is the principal quantum number. So we're talking about n is equal to 5, and D represents the second principal quantum number, L. And remember, there was S, P, D, and F corresponding to 0, 1, 2, and 3. So if this is a d orbital, then L is equal to 2. So if L is equal to 2, what are the possible values for M sub L? They go from minus L to plus L. So minus 2, minus 1, 0, plus 1, and plus 2. So if we were listing the sets of quantum numbers for these, you got 5, 2, negative 2, 5, 2, negative 1, 5, 2, 0, 5, 2, plus 1, and 5, 2, plus 2. Each of those orbitals has a separate set of those quantum numbers. It's kind of like an address, right?
Or maybe like a hotel?
Yeah, we'll get to the hotel. Yeah, the Quantum Hotel. It's a discount resort for electrons in Mrs. K's chemistry land. We'll get there. So how many 5D orbitals exist? 5. Here, each set of quantum numbers is supposed to specify an orbital, but there's one quantum number that's not allowed in each set. There's a mistake. Replace the quantum number that is not allowed with one that is. Let's start with the first one. So here, n is 3. Well, n can be 3. If n is 3, can L be 3? L can be 0 up to n minus 1. And M sub L can be negative L up to positive L. So if n is 3, can L be 3? No. What's the most it could be? 2. So if it's 2, then our M sub L of plus 2 would work. If we picked 1 here for L, or 0, then this one would be wrong. Okay, let's look at this one. So n equals 2, L equals 1. Does that work? Yeah, because L needs to be 0 up to n minus 1. So this is n minus 1 is 1, so it's at that upper limit, but it's okay. And L is 1, can M sub L be negative 2? No. What could it be? Negative 1, negative 0. Negative 1, 0, or plus 1. So, negative 1, there's actually 3 possible correct answers for that one. Depends on how the question is phrased. This one says replace the quantum number that is not allowed with one that is allowed, so they're not expecting all of them. If n equals 1, can L equal 1? No. What does it have to be? 0. And does that work with M sub L being 0? Yeah, it does. Now that we've got that settled, we can explain atomic spectroscopy. So each wavelength, each colored line in the atomic spectrum corresponds to an electron transition between orbitals. If the atom absorbs energy, it goes to a higher energy state. We say it's excited because it has extra energy, right? The excited state is unstable. I mean, nobody can stay excited all the time, right? Sometime you're going to crash. So the excited state can exist for a period of time. It's unstable. It will eventually relax down to a lower energy level, a lower energy orbital. And when that happens, a photon of light will be released that corresponds to the energy difference between the two orbitals. So energy in, the electron goes to a higher level, and it comes back down, energy goes out. And what we're seeing in the atomic spectroscopy, or the atomic spectra, is we're seeing the transitions where that photon has energy that corresponds to visible light. So we're thinking about this as, okay, the electron was in an orbital in this principal quantum number 1 level, so level 1, and it absorbed energy and it moved up to n equals 3. It can't stay there very long. It's going to go back down. It could go back all the way to level 1, or it could go back to level 2. But those are the only possibilities, because like a ladder, you can't be in between the rungs. You can be here, or there. And when this comes down, energy has to go out, because energy is conserved. Any questions? So if we look at the wavelength of this light, we can calculate its energy, and we can calculate the difference in energy between those two orbitals. Kind of cool. So in order for an electron to go to a higher energy state, it has to gain the correct amount of energy that corresponds to the difference in those energy levels. Electrons in high energy states are unstable. They tend to lose and go down to lower energy states. Each line in the emission spectrum corresponds to the difference in energy between two energy states. So that's kind of a summary. So the wavelengths of the lines in the emission spectrum of hydrogen can be predicted by calculating the difference in energy between any two states. So if you have an electron in energy state n, then there's n minus 1 possible energy states it can transition to. So then it can generate n minus 1 lines. That's like, that actually doesn't mean that much to me. We'll just ignore that one. So both the Bohr model and the quantum mechanical model predicts the lines for hydrogen very well. But hydrogen is an exception. Hydrogen has one electron and only one electron. So we can look at the energy of the photon that's released as the difference in the energy levels. So this change in energy is equal to the final energy of the electron minus the initial energy. And we could calculate that using negative 2.18 times 10 to the minus 18th joules times 1 over n squared. So this is the principal quantum number of the electron. So this is where it started, the final, and this is where it ends up. No, final is where it ends up. This is where it ends up. This is the final one, and that's the initial, because delta, final minus initial. So we can simplify that equation and end up with this. This can get a little confusing with negative signs, because we can talk about the change in energy for the atom or the change in energy for the photon, right? So when a photon is emitted from the electron, from the atom has lost energy, right? So its energy is going to go down. But can the energy of a photon be negative? You can't have negative. It's like negative speed. You can't do that. So the photon energy is always going to be positive. And delta E for the atom is going to be negative because we're going down. The change is negative. And we know that lambda is equal, the wavelength is equal to hc over E. It's just a rearrangement of an equation we saw earlier. So these are energy transitions in hydrogen. So if we were to ionize, pay attention here because there's a question on the worksheet about this. If we were to ionize the hydrogen atom, the normal state for hydrogen is the electron in the lowest level, which is n equals 1. When you ionize a hydrogen atom, you take its electron away, right? So as you go higher in these levels, the electron is getting further and further away. So we could say that when it's removed, it is at level infinity. So ionizing an electron, ionizing a hydrogen atom would be going from n equals 1 to n equals infinity. So here we're looking at the electrons returning to lower states. These are the 3 that are in the visible region. And these correspond to transitions from 5 to 2, 4 to 2, and 3 to 2. There are other transitions. There's 5 to 3 and 4 to 3. But we can't see these because they're lower in energy. That's in the infrared spectrum or region. And then these transitions are higher in energy, going from 5, 4, or 3, or 2, all the way down to n equals 1. These are higher in energy, and so those are in the ultraviolet region that we can't see. Any questions? Yeah.
So electrons only to give off light that we can see.
Yes. Only these 3 transitions give off visible light. There are a whole bunch of other transitions, but they're not in the visible spectrum, right? So we can't see them when we shine that through a prism. Yeah. They could be measured other ways, though. Now this is good. Which transition emits light with the shortest wavelength? Let's talk about, something here first that I don't think I mentioned. There we go. As n gets bigger, the distance between the levels gets smaller and smaller and smaller. So it's like you have a weird ladder, and it has, you have to make really big steps down here, and then as you go up to the top, they get closer and closer and closer and closer and closer together. So that's something to remember. So here, which transition emits light with the shortest wavelength? Well, we're envisioning these things in terms of energy, right? So we could, kind of draw these. Well, I think I can. Let's say that's 1, and this is 2, and this is 3, and this is 4, and this is 5. So we're talking about 5 going to 4, 4 going to 3, or 3 going to 2. Which one of these has the smallest energy? This one, right? Those are the closest in energy compared to these other ones, because 1 to 2 is a bigger energy change than 2 to 3. And as you go up, they get closer and closer together. So this is a small energy change, and this is the biggest energy change. But we have to think about the wavelength. Which one has higher energy? The top one. That's high energy, this is low energy. So the high energy one has the short wavelength, and the low energy one has the long wavelength. So if we're looking for shortest wavelength, this is shortest wavelength, we're looking for the highest energy, which would be 3 to 2. Whoops. Whoops again. There we go. And you'll get to practice that on the worksheet as well. Okay, determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So we've got n equals 2, we've got n equals 7, and they're asking us to find the wavelength. Well, we had this equation that the change in energy was equal to negative 2.18 times 10 to the minus, I think it was 18 joules, times 1 over the final n squared minus 1 over the initial n squared. And we know that the energy of the photon is equal to hc over lambda, which rearranges to lambda is equal to hc over E. N equals 2. Is that the final or the initial? Initial. This is going from n equals 2 to n equals 7. So this is the final one, and this is the initial one. So we've got 1 over the final, which is 1 over 7 squared, minus 1 over 2 squared. And please do not find a common denominator and subtract those fractions. Just type them into your calculator just the way it is, and your calculator's fine. So negative 2.18 EE minus 18 times, and I'm going to open the parentheses, 1 divided by 7 squared minus 1 divided by 2 squared. Close the parentheses, equals. So this is equal to 5.01 times 10 to the minus 19 joules. Here, delta E is positive because the atom is absorbing the energy. The electron's going to a higher energy level. So this photon comes in. We want to know the wavelength of this photon. So that's going to be H times the speed of light divided by this energy. And what happens to the units? The joules cancel and the seconds cancel, and we get meters. So 6.626 EE negative 34 times 3 EE 8 divided by 5.01 EE negative 19. My calculator is showing me this, and it got paused in there somewhere. Oh well.